Hello, I'm Doug Montgomery, and I'd like to welcome you to our first Fireside Chat of 2022. And hopefully you're getting used to writing down 2022 instead of 2021 whenever you have to write the date down. I'm just now getting tuned into that. For those of you who have not been around much on our course, we run these monthly Fireside Chats to provide some interaction with the MOOC participants. I always have a guest speaker, and we talk about specific topics or applications of experimental design methods. We always leave some time at the end for Q&A. This is a great time for you to bring up any questions or things that you are interested in. It could be a question about the course material itself, or it could be a question that's specific to a situation or an application that you're interested in. For those of you that are actually on Coursera, we post the Fireside Chat recordings to the course, and you can find them in the Resources tab of your course. And all of the Fireside Chats that we have done since the very beginning are there. And I would encourage you to look at them. We've had some really interesting guests and some really interesting presentations that I think you would really enjoy taking a look at. Quick reminder about how we operate things. Please continue to keep your microphones muted and your cameras off during the session so that we don't have a lot of background noise that would disturb things. And if you want to send in a question to either me or to our guest, please do that using the chat function on Zoom. We have some questions that have already been submitted, but you don't need to wait until the Q&A portion starts, which will be about 30 minutes into the Fireside Chat. You can submit them anytime. You can type them into the chat function on Zoom, and we will do our best to get to them during the session. If we don't get it taken care of during the session, then we'll look at it offline and respond to you in Coursera for those that are enrolled in the course. My guest today is Dr. Amy Braverman. She is the principal statistician at JPL, the Jet Propulsion Laboratory, California Institute of Technology in Pasadena, California. She's the technical group lead for Statistical Methods and Applications in the Uncertainty Quantification and Statistical Analysis group of the Instrument Operations and Science Data Systems section. She has a BA from Swarthmore College in economics. She worked for about 10 years in litigation support consulting, and then returned to graduate school at UCLA in the early 90s. And she got an MA in mathematics and a PhD in statistics. And she started her career at JPL as a postdoc in 1999 and has been at the lab ever since. And her early work was in the use of data compression methods for the analysis of massive data sets. She's also worked in spatial and spatiotemporal statistics, statistical methods for the evaluation of climate models. And most recently, she's been involved in this field of uncertainty quantification. She's been at the forefront of JPL's efforts to bring rigorous uncertainty quantification techniques to the derivation of geophysical information from remote sensing observations collected by NASA and JPL instruments. She particularly enjoys mentoring postdocs and young researchers and building the capability in statistics at JPL and collaborating with academic colleagues to connect their research and that of graduate students to JPL and NASA problems. I am really delighted to have her as a participant because the folks at JPL do a lot of really interesting and exciting things, and you're going to hear about some of that in Amy's talk. So Amy, the floor is yours, and you can start anytime you'd like.
Thank you, Doug. It's a pleasure to be here. My only wish would be if I could be there with you in front of that beautiful electric fireplace.
Yeah, we often have another chair sitting right here, and we could be face to face, but the times are not right for that. But hey, you can, you know, when things settle down, you can come back. You know?
I would love to. I
by quite a few guests that I would like to have repeat performances from, and you're one of them. So
thank you. Thank you.
We'll do that.
Yeah. Okay. So thanks for the introduction. I am actually not going to talk about experimental design today. What I'm going to do is I'm going to talk about a problem that we have at JPL where I think experimental design should play an important role. But we haven't done that yet because we don't have experts in experimental design at JPL who could help us with this problem. So I approached Doug after meeting him at a conference, and of course, his reputation is worldwide and for all time as the man in this area. And so I will say shamelessly that I'm actually using this time to introduce the problem to Doug and all of you in the hopes that we can get some help, and maybe I could learn something about experimental design.
I'm easy to recruit. I would love to work with you folks.
Very good. Let me go here. So can you see my screen? Is my screen visible?
Yes, I can see it.
Okay, great. So as Doug said, at JPL, our job is to build and fly spacecraft for studying properties of the Earth, the solar system, and the universe in general. I work mostly in the Earth science area, so we build and fly spacecraft and spaceborne instruments that look at the Earth and attempt to collect data about it. And then we do a significant amount of analysis on those data ourselves. But our main job is to produce data sets for the international science community to do their science. So what I'd like to talk to you about today is uncertainty quantification and how it is applied in the process that takes the data that the spaceborne instruments collect and turns it into actual geophysical data that scientists can use. And it probably won't surprise you to hear that that process involves a tremendous number of transformations and other data handling that confer uncertainties on the information that we're processing. And the topic of the science that most people are interested in involves inferring unknown quantities from the data that we present them with. So uncertainty quantification is embedded throughout the data collection, processing, and analysis phases. So here's just a quick outline, and I'm going to end up down there at the bottom with some implementation challenges and some top-tier research problems, which is where DOE comes in, and I will try to explicitly point out where that's an issue. So let me just move here. Here's just one quick slide on remote sensing. Let's imagine that we have an instrument, which is essentially a giant camera that is orbiting the Earth. Typically, these instruments orbit from pole to pole as the Earth turns underneath it. And as the instrument flies along, that's the observer here, it's looking down at a scene that has a ground footprint, which is this little pixel here. And for the sake of the discussion we're having, let us imagine that that this is a passive instrument, meaning that the sun illuminates the scene, as shown on the left there, bathing the whole scene in photons. Those photons, as they pass through the atmosphere on the way down, encounter little aerosol particulate matter and water vapor and other gases in the atmosphere, causing some of those photons to scatter and some to be absorbed. The ones that make it to the ground, some of them are scattered and some of them are absorbed, and some of the scattering gets bounced back in the direction that the spacecraft is looking, and those photons are counted. And what the instrument does is essentially partition all the photons that arrive that are attributable to that pixel there into what's called a radiance spectrum. In other words, it kind of sorts the photons into channels where the intensity of the energy in a particular channel is recorded in the form of a photon count. So the result of this is something that you see on the right there called a radiance spectrum, which has the x-axis is the wavelength, and actually these are very small but discrete little wavelength bins. And that radiance measurement, the vertical numbers there, have to do with the amount of energy or the number of photons that actually got partitioned into that little bin. So you could think of this radiance spectrum as belonging to this pixel over here on the left that is sort of shaded and highlighted there. So another way, probably a good way to think about this, is that the spectrum can be thought of as a very high dimensional vector. In this particular case, there might be 2,000 different little spectral bins along this axis. And so each of these values goes into a different bin and would be represented in one element of a big vector. The red, green, and blue lines over there show you where the visible wavelengths are, but there's much more information available here because we have all of these wavelengths, not just those three. Oops, see, why advance? There we go. Okay, so what happens when a collection of those radiances arrive from space at the ground? They have to be processed in order to turn them into geophysical information that scientists can use. So we have some nomenclature for this. The raw photon counts that come down from the satellite are called level 0 data. And imagine a big spatial field covering the scene of many pixels and a radiance associated with each of those pixels. Those photon counts that are the raw input have to be sort of cleaned up a bit before we can do something with them, meaning georectified means attaching a ground location to the particular radiance vector, and calibrated means kind of fixing them up to make sure that we account for things like the fact that the detectors in different pixels might not be equally sensitive. We need to adjust for that. The big important, in my view, processing comes along when we take that level 1 and we stuff it into something that's called a retrieval algorithm, which I'll explain in a minute. And that algorithm outputs estimates of geophysical state. So if I start with a radiance vector like what I showed you earlier, what will come out of our level 2 algorithm might be something like estimates of surface temperature in each of the pixels of the scene, or the amount of carbon dioxide in the atmosphere above each of the pixels in the scene, that sort of thing. There's further processing that's sometimes done. That's not, we won't talk about that, but just for completeness, the data sets that are delivered from these geophysical state algorithms can be very, very large. They're typically processed in pieces. Every time the satellite dumps something down to the ground, that set of pixels is processed. And so you can have millions of files with very large amounts of data in the files, and that's inconvenient for science analysis sometimes. So people do they make what are called level 3 data sets, which are so-called statistical summaries. The simplest way to make a level 3 data product is to take all the geophysical data from a given month and partition it according to its location on, if you're making a global data set, on a global grid, so a 1 degree latitude by 1 degree longitude grid. And then you might put the mean value of your derived geophysical variable like temperature into each grid of each cell of the grid. And if you're on it, then you'll also accompany that with maybe the standard deviation of values. But that's pretty crude. We don't actually like doing that, but that's how some people do it. And further, sometimes these geophysical data sets, either the level 2 or the level 3, are input into physical models like data assimilation models to derive yet other things, and those are called level 4 data. But the main takeaway from this is that level 2 data aren't really data in the sense that a statistician would collect data. They are inferences based on the level 1 data. So when drawing conclusions or making policy decisions using these level 2 data products, it's crucial to understand that these are not, that these values that you use are the result of a whole pile of earlier processing or transformations, and therefore they're subject to uncertainty. Never mind the fact that the original radiances were collected, or the original photon counts may also be subject to some amount of uncertainty. So, excuse me, it's really important to keep track of the uncertainties that are imparted to the data. So here's another view, kind of a notional cartoon view of a remote sensing observing system. The things in gray on the left are sort of mental constructs. We don't actually get to see those. The things in blue on the right are things we get to see. Imagine that in a given pixel, we start with a true state of nature, and that nature has some function that we'll call a forward function that converts that true state of nature into radiance. And you can think here of radiative transfer, which is the study, the physics of how photons are scattered and absorbed by different media. So when the photons, the nature has a state, let's say that that state is the amount of CO2 in the atmosphere above a certain pixel. Nature has a forward function which says, well, if this is the amount of CO2, and we probably have to specify other things as well, like the amount of aerosol particulate matter and the amount of water vapor in the atmosphere and what the scene type is, then what you would see, the radiance vector that you would see would be this y sub 0 that I'm referring to here. That was like the radiance vector that we saw in the picture, except that it would be a noisy radiance vector, meaning that the instrument itself isn't completely accurate. Sometimes there are artifacts due to just the measurement system. And so what we'll eventually end up with is a noisy observation Y. And this is what arrives at the ground. And after level 0 and level 1, level 0 and level 1 processing, we end up with this cleaned up radiance vector Y, which we put into this algorithm that we call a retrieval. And it's called a retrieval because it aims to, quote unquote, retrieve the true state of the atmosphere X from the noisy observation Y. And the retrieval algorithm is a very complicated function that incorporates another forward function that I call F1 here to distinguish it from F0. F1 is our best understanding of what we think F0 is. And of course, we don't know it, because if we did, we wouldn't need to do any of this. We would have all the answers we need. But the important thing here is that the output here is a state estimate, this X hat, which claims to be or wants to be an estimate of the true state that went in. We're not going to bother with the rest of that. So the retrieval problem is to, if you think like a Bayesian or think in conditional probabilities, the retrieval problem says, let's try to, let me go back here, let's try to derive our X hat, our state estimate, as the conditional distribution of the true state given the observed radiance vector Y. But the uncertainty quantification problem is a little bit different. The uncertainty quantification problem says, no matter how you do that retrieval, no matter what method you do, what we'd really like to know is the conditional distribution of the true state given the state estimate that we actually computed, because there were a lot of things that went into the computation of X hat that we would be ignoring if all we did was look at the distribution of X given Y. So we want to make use of all of that. So essentially uncertainty quantification here boils down to trying to determine what the probability, the posterior probability of the true state is after we've seen the estimate. And we can do this pixel by pixel. So uncertainty quantification provides a formalism for understanding uncertainty in the output of computational models. Remote sensing data processing, like I just described, utilizes lots of complex computational models, like the retrieval R, which has embedded within it that forward function F. But we lack lots of information about the uncertainty on the inputs. There are many unknown unknowns. This is a really big problem because our model F is only our best understanding of how nature works. It's not real nature. And in order to make this whole thing, this whole data processing enterprise be able to keep up with the data that's coming down from space, we have to make certain computational compromises that will also impart uncertainty to our answer. When we originally started thinking about how to do this, we had a slightly different, we had one additional mandate, which was the retrieval algorithm. The ground processing system was already in place. We were not allowed to design a new one that might have kept track of the uncertainties along the way, nor were we allowed to change anything about the way the data processing system was performing or done. So the entire thing we had to do here was after the fact. That's just a little thing. So let's talk about uncertainty quantification now. Here's my favorite cartoon of uncertainty quantification. It came out of this nuclear engineering journal paper down here at the bottom. I like it because it covers not just what is uncertainty quantification or how is it done, but it also covers two other things that end up being really important to most applications, and particularly engineering applications, which are validation and verification. So you may hear of VVUQ as validation, verification, and uncertainty quantification. And as originally conceived, you might say that uncertainty quantification, validation, and verification were all kind of aimed at assessing the quality of the predictions produced by this computer code up here. So this might be our retrieval algorithm here, might go in there. And you can imagine assessing that using a Monte Carlo simulation, which is what's represented by this forward UQ ellipse here, where you assume some sort of distribution on the inputs that go into your computer code. You sample repeatedly from that distribution. You push each of those samples through your computer code. So you start with an ensemble of inputs, and what you get is an ensemble of outputs. And the spread of that distribution of outputs is a measure of the uncertainty imparted to the inputs by the computer code. Just for completeness, validation is often defined as the comparison of those computer model predictions against examples of reality, sometimes found in experiments or just going out and having some ground truth data. Verification is loosely defined here as the act of making sure that the way your mathematical description of the way the process you're trying to mimic works is properly implemented in the computer code. And that leaves one box here that I haven't explained called inverse UQ, which has to do with how you obtain this input uncertainty distribution. This is a key part of the uncertainty quantification enterprise because often we don't really know. There are many things you can do, especially if you have some ground truth, some reality available to you, to try to reverse engineer what the distribution is on the inputs to your computer experiment, or you can just ask an expert to take a guess. Oops, so, right. This is a picture of the exact same thing, but I've stripped out the verification and validation part, and I've left behind only those things that I think are important for uncertainty quantification. And I've added a little bit of notation to the problem here. So here's our distribution of inputs. Now we're going to call the inputs to our complicated model. It's called the model F. Inputs are called theta. We have some distribution of theta. We sample repeatedly from them. Those are the theta stars. We push that through, and the output is, let's call it Y hat here. Our ensemble of outputs generated by applying the computer code to our ensemble of inputs. And then there's this other part of the problem here, which is how do I try to understand what that distribution is? Well, like I said, if I have some actual direct ground truth observations of the thing that I care about, these are the YRs for real, then I can use that to try to infer what the posterior distribution of the outputs given these YRs are. Another thing that we might want to notice about this picture is that if I'm going to do this whole enterprise, what I would like to do is actually make use of the outputs of my computer model in doing that, in trying to understand what that distribution is. So now those Y hats are over here along with the IRs. And the other thing is, well, if I had the ability to figure out what this distribution was, what I might do is think of the inputs, instead of just calling them theta, I'm going to split them into two pieces. X might be a critical input that I really care about, and theta might be what let's call them nuisance inputs, other things I don't really care about, but I have to have in order to make my forward model run or my model run. If you're in the remote sensing business, it's important to distinguish between those two things. An earth scientist actually might care about the distribution of this key input. Like, for example, in our earlier pictures, we had that true state vector. So maybe the true state vector is an input here. to our forward model, which converts those true state vectors into, let's call them fake radiances over here. But I can get that by integrating the not interesting values out of this probability distribution that I obtained through this scheme here. But I don't think that's actually the right picture for us. I think the right picture for the problem that I described, the retrieval problem, has not that forward model up here in the corner, but has the retrieval algorithm up here in the corner, because this is the thing we're going to be applying routinely. So recall that the input to the retrieval algorithm were radiances, which there's our y, our radiance, and there were other things that our algorithm needs to run. I had called them B's on that earlier slide, but I didn't highlight that. But it's not enough just to put the radiance in order to run the forward model. You have to tell that, I'm sorry, the retrieval, you have to tell that retrieval algorithm other things like what the atmospheric properties are, how much water vapor was in the atmosphere, because remember that the photons are getting scattered not only by the thing we care about, either the surface property, the atmospheric property, but also by nuisance quantities like I said, there were those aerosols in the atmosphere, other things that scatter the photons. So now distinguishing between the inputs y and theta star, we're doing the same Monte Carlo experiment where I'd like to have an example. I'd like to have some examples that I can draw from, distribution I can draw from that gives me the joint distribution. It's really of the nuisance variables and the actual input y, but in this case, the true state vector sits behind the radiance vector. Remember, we had that forward model, that forward function f that converted the true state into an observed radiance vector. Well, that's the role here. And in principle, what I'd really like to get here would be if I had the distribution of the nuisance inputs and the real inputs, x here, and I converted x into a corresponding y, and then I did the job here by sampling from the sampling synthetic realizations of theta star and y star, then I could get my ensemble of estimated outputs, and perhaps I can then get about the question of understanding how good my computational model for this inference really is. I do have at my disposal some true ground truth observations here. I'm calling them XRs here. And the YR in this case is actually the radiance that we actually got from the instrument. So you can think of a big conceptual experiment here where we have some synthetic, we have some truth values over here. We can use this sampling scheme to infer a distribution on the inputs, and then we run a big Monte Carlo experiment here to try to get not just a single point value, but an ensemble or a distribution of these x hats for a given y that we ended up putting in from our sampling procedure. Inverse UQ is a tough nut to crack here. Getting this distribution is hard. And I think maybe I should just leave it at that without going into greater detail. So let's talk about some challenges here. The things in purple on the next set of slides are the things where I think DOE could provide a crucial information, crucial help to this enterprise. Like I said, formal DOE does not play much of a role in any of this, but excuse me, I think that it could and it should. Let's see, how do I want to say that? There are very computationally expensive aspects of running the simulation experiment that I've outlined. One is that this retrieval algorithm, this computer code, can be very expensive to run and take a long time, especially when we're dealing with high dimensional inputs to it. Now, those would be some of those nuisance variables, the true state that we're actually interested in, and those radiance vectors, which I already showed you one that was 2000 dimensional. This can make running this retrieval algorithm extremely expensive. And not to mention the fact that for all of these quantities, we don't just do it once. we have to do it over and over and over again. We're not just doing one pixel, we're doing a whole field of pixels. And every 5 seconds, we get a new field that we need to process. So this can be extremely, extremely slow to do this with typical means. So sometimes what we try to do is build an emulator for this function R, which is a statistical or machine learning model that can mimic what R does without having to go through all the physics calculations. And it's deceptive here because the process of building that emulator can be itself expensive, but we really need help with this. We need help in how to build these emulators. We have people working on that. What it should do is mimic the behavior of R, but be much faster. Let's see here. I alluded to this problem here. This is extremely computationally intensive. The inverse UQ, if it wasn't extremely computationally intensive, then notice that we would be able to solve our problem entirely through inverse UQ. We would simply try to obtain this distribution, and here's the X we care about right here. We could then integrate Y and theta out of this distribution, and we'd be done. We wouldn't even need R if that were the case, but it's not. This is too hard to do on an operational basis. So that's why we have R in the first place. The direct observations of the true process can be very sparse. That's over here. While we have radians, we have lots of radiances that we need to process. The places around the world where there are ground stations that can give us information about what the truth is that we can use to kind of calibrate this whole process. Just to give you an example, for carbon dioxide measurements for the Orbiting Carbon Observatory 2 mission, there are 7 stations located around the world where we can get this ground truth. And that's just, you can't begin to say how inadequate that is if you were to try to leverage these ground observations in some systematic way. So all you can really do is evaluate how well you're doing at the places where you have that ground truth and call that the answer, which is what has been done in remote sensing typically, but that's not very good. We think we can do better than that. Finally, the number of Monte Carlo runs of this whole system, in other words, the number of samples we take from this box here, has to be huge, because this computational model is operating in a very, very high dimensional space. So we have to do this so many times, it's not even funny. So DOE can help us in a number of ways here. Let me see if I am, not yet, right. DOE could help us in at least 2 different places in this enterprise. One is this sampling exercise here. If we want to get a good ensemble that tells us something about the uncertainty that relates to R here, how should we take these samples from this distribution? Let's say we knew what this distribution was. How should I sample from it? What are the most informative places to take samples from this distribution in order to make sure that the ensemble is a good representation of the uncertainty that we have in the computational model R. The other place where this can help us a lot is in the design of these emulators, the training of these emulators. What that entails is having examples of inputs and outputs to R, and then building a statistical model that gives us good predictions of what R would have done if we actually had run the real R. But in order to design a good emulator model for R, we have to cover the space of inputs. This should start sounding like DOE now, because we can't run it everywhere. Typical strategies are just to put some grid on all the possible values of our theta star and our Y star here, and just run the full-on model R for those particular inputs. But we all know that's not efficient. Doug knows that's not efficient. So the research problems here are particularly in how we can do a better job of designing the emulators more efficiently, and then how to do a better job of deciding what to sample out of our potential draws from this distribution in order to get ensembles of x hats that properly represent the uncertainty characteristics of this R function. So I'll leave you with this thought. DOE for this talk here, for our conversation, is the important part of this. Getting these emulators and these sampling strategies together. And I put the word dimension reduction here because all of this is so high dimensional that maybe our design of experiments, maybe everything has to be done in a space where the dimension has already been reduced first. And that may add another layer of interestingness to our DOE problem. So to close up, let me say we need emulators that run in low dimensional spaces and that are trained using robust and non-parametric, and I see a spelling error there, sorry about that, design of experiments. Non-parametric means not assuming things about the distributions from which the data came. So I think I'm going to stop there. I hope I'm not over time. But that's what I got.
Yeah, you're right on time, and this is a really interesting talk.
Good.
I have to admit, some of this it really would require a lot of thinking, to figure out how to implement experimental design.
Yeah.
But one of the things that I can think of right away in terms of building these emulators is using space filling designs.
Yes.
You mentioned a grid. Yeah. And that grid approach can work, but depending on the dimensionality of the problem and the fineness of the grid, you can have a massive number of combinations to run. Yeah. And if your underlying computer model requires a lot of time, that becomes really not very feasible. And space filling designs are an alternative to that. And they can be very efficient, and there's a literature out there, and there's other work that can be done, and I would think that would be a place to start with that part of the problem. But this is absolutely fascinating stuff, and I think there's actually some real research problems.
I think there are too.
Not necessarily research from your end of the picture, but from my end of the picture as an experimental design person.
I'm with you. I mean, I completely agree with you, which is why I wanted to give the talk. And we do have a postdoc who's working on an emulator for the Orbiting Carbon Observatory mission, and he's been dabbling around a little bit with. He went to Latin Hypercube.
Yeah. Place to start
for this, and it made a big difference.
Yeah.
My goal is to get you sufficiently interested in this that you and maybe a student who's also interested in it would want to work with me and that postdoc and others at JPL to maybe think from the ground up, throw out everything and let's just channel that Doug Montgomery thought process and think about, what can we do here that one of the big hangups is we can't assume things are Gaussian. We absolutely can't, right? And it would be really neat to think about if there's something new and out of the box here, that could be brought to bear on the problem. I mean, I'm surely there are better ways, even with existing methods, to sort of decide how we do these things. One thing we haven't grappled with at all was this question of how to sample.
Yes.
There was that sampling box, not the emulator. Forget the emulator for a second, but the whole idea of how to sample. Typically what we do is we typically try to stratify geographically so that we get some sort of broad representation of the kinds of radiance vectors that we might encounter. But it's also true that if we do that, it's interesting because the retrieval algorithm is extremely sensitive to subtle differences in certain wavelengths.
I see.
So if you simply kind of take an agnostic approach and say, I want to make sure I've got a broad range of kinds of radiances, it may not be the case that, how do I put this? What constitutes a broad range of radiances might not be radiances that somehow uniformly cover some space, because it's the small absorption features. I call it the small wiggles problem. There are small wiggles in these spectra that have an enormous influence on what the ultimate inferred value of the geophysical property would be. So you're working to begin with in some warped space. You could think of it as being in a warped space where small changes in certain parts of the spectrum matter a lot more than big changes in other parts. So there's sort of that angle as well.
Yeah, and that tends to make me think that, again, some type of stratified sampling approach is the right way to go.
Yeah.
And that is itself a big subject.
Right.
There's lots of different ways to do stratified sampling, but I can see that that's an avenue that definitely should be explored. And you don't have to worry about getting me excited about this, because I'm on board, and I may even have a student coming along that would be interested in this. She is currently a master's student, and she's doing her master's thesis on an experimental design problem, but it's more of an analysis thesis. The design problem that she's starting with is, we already have a solution, but now we're trying to figure out how to analyze the data. So she's working on that. But she's definitely planning to stick around for the PhD.
Excellent.
And she's really smart, and she's very interested in this whole area of experimental design. The only thing that might be an issue is she's not a U.S. citizen, and I don't know whether that creates issues on your end or not.
It does not at the level of an academic collaboration. It may have some impact on whether she can come visit us or not, and the kind of information that we can share.
Right.
But this is all sort of theoretical stuff. There's nothing.
That's the way I would see it, and I don't think there would be any real big problems with her individually. So yeah, she might turn out to be a really good person to try to wire into this, because my guess is she'll be finishing her master's thesis this summer. So she's sort of on track to get moving into the PhD program. And
outstanding.
She would be, and as long as I don't die or something, we'll be.
Let's hope not.
Well, you get to be my age, you wonder, I look at all these famous people that have died, in the last, year, and John Madden, 85 years old. I don't think of 85 as old.
Yeah.
So it does make you wonder. Amy, we have some questions. We've got 3 that have already rolled in, and let's take a shot at looking at these questions, and any help that you can give me in answering these, I would greatly appreciate it. Sure. I'm going to read the question. Okay. This is a situational question. And the person says that I am working on a process with many factors, 20, and I want to reduce these factors before doing the experiments. How can I do that? Okay, so that's step 1. And then in the process, my response is not a numeric value, but it is satisfaction, which I can measure through questionnaire. And then I have a score level, which is a numeric value. And my question is, can I consider that score like a numeric response without any conditions? Okay, so let's do the first part of this first. How can you reduce these factors before doing the experiments? Well, of course, the classic way to do this is to run a screening experiment first, and to reduce the number of factors from X to Y by looking at which factors are significant in the screening experiment. Now that sometimes gets difficult to do depending on the situation. Let me give you a practical example. Okay, I've been in the wine business since 1984. And when we started our first winery in Oregon, we were growing grapes, and we were going to try to learn how to make Pinot Noir. The only problem is none of us were winemakers. Okay, but we were engineers, and one of the guys was a chemical engineer, and he was our winemaker, and he said, we learned how to make polymer by running design experiments. And so we decided that's what we would do. But we had sort of exactly the same problem that this person does, in that we had a very long list of maybe 15, 20 factors that we could potentially use as design factors. And some of them were things that we were fairly sure were important, and others were things that we didn't know about, that just the folklore of the industry told us that might be important. So here's what we did. We took those 15 factors, and we down selected using what we knew about the problem, and we down selected to 8 factors. And you say, why 8? Well, it turns out we could afford to do 16 tests. Okay, and if you have 8 factors at 2 levels with 16 tests, you have a resolution 4 design, which means you can learn all about the main effects and maybe something about the interactions. And then we decided that we would probably be experimenting sequentially. So you do that first experiment with a subset of say 8 factors. We would look at the results. Then we would drop the factors that appeared to be unimportant. And then we would plan our next experiment by retaining the ones that were important from this experiment, and then bringing in additional factors that we didn't experiment with from the original list. And we realized we were going to have to do this sequentially. We couldn't run a big comprehensive experiment with 20 factors. We did a series of relatively small sequential experiments. Now, the problem that we had was that you can only run 1 experiment a year. Winemaking is an agricultural process, you know, and so you get 1 experiment per year, and it took us 4 or 5 years to work our way through that list. But we were really successful, because the first vintage of wine that we produced won a gold medal at the American Wine Competition. So it worked. Okay, and so I would urge the experimenter here to think about some sort of sequential approach, and hopefully it doesn't take you a year to run an experiment, but maybe you can down select a subset of these factors based on what you think you know about the problem, and that knowledge is probably imperfect. Okay, but you have to start somewhere. And so that's what I would suggest thinking about. Now, about the response not being a numeric value, well, if you have these score levels that cover a range, maybe 1 to 10, I don't think you have any problem treating those as a numeric response. I've done that for years. If you have multiple people complete that questionnaire for each of the test combinations, you can use the average of those questionnaire scores, and that's even better. That's exactly what we did in our winemaking experiments. We would have results of a 1-year experiment. We would have a panel of maybe 5 people that would taste test every one of those 16 combinations, and we would rank order them. You know, with 1 being the best, 2 being the next best, all the way on down to N being the worst. And then we would average the scores. And we analyzed those using traditional methods. And we never had any problem with that. In fact, those scores really are like ranks. And there are some papers that have been published in the literature that show that normal theory analysis methods on ranks work really, really well. So I don't think you have any problems on the second part of this. the first part is more challenging. And, what I would have to suggest is maybe thinking sequentially. Again, depends how complicated the actual physical experiment is. But I don't like to see people running great big gigantic experiments right out of the box. Amy, do you have any comments on that? Anything that you'd like to add to that?
Only that I love the wine story. I remember hearing the wine story at one of your short courses. And that's why there are grapes on the cover of the new version of your book, I think.
Yeah, there have been grapes on a lot of editions of the book.
And I guess just a couple, I do not claim to be an expert on experimental design, but a couple of things about that question did catch my attention. The satisfaction scores are in fact numerical values. Mm-hmm. They may not be nominal continuous variables, but at the very least they're ordinal.
Right.
And so I don't see that as a problem.
No, I agree with you. I think we can use normal theory methods here and not worry.
And the other thing was the idea that dimension reduction popped to mind there. Mm-hmm. As well, and that's the language I would use. But I think you answered the question.
Yeah, I think that the question here is, this is a very common problem that lots of people face, and so hopefully our discussion has really helped. Okay, next question about factorial and fractional factorial designs. I got a question about design of experiments. Of an experiment. There are 3 factors, and every factor has levels. I assume maybe lots of levels. And for each design point, experiments are carried out in a program on the computer. Aha. And the result from the program for each design point, I assume that means each run, is the same. So if you run it many times, you get the same value for each. So it's what we call a deterministic computer model. Like maybe finite element models. Okay. When applying any method, does this make a difference during implementation? Oh, yes. There are specific experimental design techniques that work very well for deterministic computer models. Space filling designs are the classic sorts of designs that are used for this. And there is some discussion of space filling designs in the course. And in my textbook, there's some discussion of these designs. And so I always think about that as the place to start thinking when you're having this kind of problem. It says that the calculations are proven to correct. The results are always the same. Okay, so the computer model produces the right answer, which is good. Fractional factorial design is currently being used. I don't think that that's the right approach. I think space filling designs are better. And then in terms of fitting models to the results, traditional polynomial models don't really work very well because they interpolate the surface. And what you really typically want here is you want an exact fit. You want an exact prediction. So when you plug in one of your design points to your model, you want that model to return exactly what you observed in the computer experiment. So polynomials are not going to do that. They're going to be interpolating functions. You should probably be looking at some sort of Kriging type model. Gaussian process models are the classic. And you can fit Gaussian process models to these experiments very, very easily. If you're using the JUMP software that we use, that we talk about a lot in the course, JUMP has the capability to create these space filling designs. There's quite a repertoire of those available, and it also has the ability to fit the Gaussian process models. And again, there's an example of all of that in, I think it's in chapter 11 of my experimental design book. So there's a lot of help to get started on this, but but I would not be using fractional factorials and the sort of traditional polynomial fits. That doesn't really work very well. And there's been some research done that really shows that the space filling designs and Gaussian process models are a much better route to follow. And in fact, I think those Gaussian, those space filling designs have a lot of potential application for some of the things that you talked about, Amy.
I absolutely agree. We've used Gaussian processes quite a lot.
Yeah.
Particularly for the emulator problem.
Yes.
And I work with a guy at Caltech named Human Owadi, who's an applied math guy who has a lot of really interesting work on both the theory behind GPs and why they work, and using them as as a machine learning tool.
Right.
Things.
And the beauty of the Gaussian process is that if you do plug in one of your existing design points, you get exactly the same answer back that you got from the computer model. And so you've got a lot of confidence that this thing, when you plug in inputs that are not one of your runs from your computer model, you've got a lot of confidence that what you're getting is something very, very close to what the computer model would produce.
Right. The benefit of the GP, though, is that it also returns an uncertainty on that prediction.
Yes.
Right.
And it's very fast.
Yeah.
It's super fast. And so this is a really interesting way. And I think maybe that this can push this individual toward thinking about this. But you will have to look at the next course in the program, which is the response surface part, because that's where this material comes up in the Coursera course. And chapter 11 in my textbook is all about response surface methods. And I sort of think of these space filling designs and Gaussian process models as response surface methods. So the person that wrote this question, move on from the factorial and fractional factorial design course in Coursera and go to the RSM course. Okay, we got one more at least here. Oh, okay. Now this is really an interesting question about the random models and nested and split plot design part of the course. He says, knowing that A/B testing is inefficient for email marketing, what has been the technique that has the best results in your experience? Well, first of all, I don't know that I've seen a lot of evidence that A/B testing is all that inefficient. Yes, there are a lot of complications in setting up the different factors levels A and B. But then there are some well-developed methods for routing people to those different websites or whatever they are. And there's a lot of work on methods for analyzing that data that is pretty interesting. I got to admit, I am not an expert in this, but one of my former PhD students is. I have a former PhD student, in fact, two of them, that actually work in this area. And I'm going to contact one of them because I know he's still doing a lot of this. His name is Edgar Hassler. And he has done a great deal of this. And I'm going to shoot this question off to him. And I'm going to ask Edgar to give me some input. And then we will get back to you on this, because this is a really good question, and I have some opinions and ideas, but I think Edgar would be a person that could give us a lot of help with this. And by the way, all of us are participants in these experiments all the time. Every time you go to a website, you're a participant in an A/B test. I'm sure of that. Amy, we're done for the day. It's the end of our questions. Thank you so much for doing this. This has been a really enjoyable talk. And we need to talk offline about how to keep going forward with this, because I'm excited about it, and we'll come up with some mechanisms to sort of help get this started. Okay, our next Fireside Chat is Wednesday, February 9. And information on that will be in the Design of Experiments Coursera course. Thank you for joining. And once again, thanks to our guest, Amy Braverman, for such an outstanding presentation. And
thank you for having me, Doug. And thank you to Megan and the other members of your staff for their assistance.
Oh, we couldn't do it without them. Thanks again.